Yes, we can. Maybe you want to go full screen. Yes, perfect. But stay there. We just have one minute to wait in case. Well, last speaker of this session is Elena ZAPPON, doctoral student in the high art group, and she will tell us about efficient solution of couple problems through DEIM-based data projection across non-conforming interfaces. So please, Elena, the floor is yours.
Thank you, Paolo. And good afternoon, everyone. In this presentation, I'd like to talk about reduced order model, especially for couple problem, especially for Hurt-Torso couple model. So to reconstruct electrocardiograms, basically using mathematical models. This is a work that has been developed in collaboration with Professor Manzoni and Quatteroni in the framework of the higher group. So this is the organization of my presentation. I will start with the reduction of the one-way couple model, giving you some motivation behind the development of this method, and then describing the principal feature of the method itself, and finally giving you some numerical results. And then I will try to explain how to extend this reduced order method to two-way couple model, as before, giving you some motivation behind the method itself, and finally a simple test cases for numerical results. So starting from the beginning, my PhD project is focused on the simulation of electrical cardiac output, such as, for example, the electrocardiograms. So basically here we want to solve a mathematical model that is the forward problem of the electrophysiology, and that is obviously a mathematical model, in principle, a couple mathematical model made of an electrophysiological model, such as, for example, the B-domain model that describes the activation of the heart electrically, obviously. And then we need to couple this electrophysiological model with a Laplacian inside the torso, so a torso diffusion model. After we have solved this couple model, we can simply record the solution of this model in some specific location on the surface of the heart to obtain the electrocardiograms, or if we want to do the electrograms, we can do the same, considering inside of instead of the torso a small, for example, domain around the heart itself. So there are different ways to do this coupling. From now, we will consider a one-way coupling. So basically, we are assuming that the heart is completely isolated, so that we can solve the B-domain model only on the heart. And then we can use the solution coming from the B-domain model at the interface of the two domains that here obviously are the heart and the torso as boundary condition for the Laplacian on the torso itself. So here we are applying basically Dirichlet boundary condition. This is obviously a very expensive model to be solved, and we would like to reduce the computational cost using reduced order model. And in particular, our reduced model need to take into account the parametric dependency of this model, both for the physical parameters that are inside this model, but also on the time, because in reduction time is a parameter. And in particular, given that the B-domain model is a time-independent model in these couple models, also the Dirichlet boundary condition are time-dependent. So we can consider this Dirichlet boundary condition as parametric Dirichlet boundary condition. And moreover, we would like to reduce the computational cost, going also to change how we are going to discretize the domain of the torso using finite element methods. Basically, we would like to use a smaller discretization than the one that we are using for the heart inside the torso. But doing so, we are introducing a non-conformity of the meshes at the interface of the two domains. To treat this problem, usually, for example, in our group, we do a post-processing procedure in which we extract the solution at the interface from the B-domain. We save this solution in specific files, and then during the torso resolution, we read this information from the external file, and we interpolate geometrically this information. This is a very expensive procedure. This is, for example, one possible simulations. And so obviously we would like to reduce the computational cost, in particular find a way to reduce efficiently this type of couple model, considering parametric data, Dirichlet data, to be exchanged at the interface of the two domains that we are considering. And moreover, we would like also to take into account the possibility to have non-conformity at the interfaces of the grids at the interfaces of the two domains. To do this, we have developed a method that in principle can be applied to all kind of one-way couple model coupled with Dirichlet boundary condition. So to explain to you how this works, I put myself in a more general setting. So we consider two different parameter-dependent model that we call master and slave model that are coupled with the Dirichlet boundary conditions. And we can solve these two models in two different domains with a common interface in which the domain can be of 3 or 2 dimensions. It's not very important in this case. And we are going to reduce this couple model considering reduced basis methods, in particular modular methods, in the sense that here we are going to reduce separately the 3 parts that made this model itself. So first of all, we reduce the master model using classical technique. This is very classical. We use proper orthogonal decomposition, and in case of need of hyperreduction, we use the discrete empirical interpolation. Then the most difficult part is the treatment of the interface condition. For this, we are going to reduce the dimension and at the same time to interpolate the interface condition using the discrete empirical interpolation. And finally, we are going also to reduce the slave model independently from the other step, using as before proper orthogonal decomposition and eventually discrete empirical interpolation. So you can see that all these 3 steps can be done independently one on another. And also we can, for example, reduce only part of the system and solve the other part considering a high fidelity solution. So just to give you more detail, I will go very fast in the reduction of the master and the slave model because these are quite classical. So basically the master and slave model, and in particular here the master model, can be reduced. Consider, for example, proper orthogonal decomposition. So we have an offline phase that is done only one time, and this is very expensive, in which we are trying to do the training of our reduced model, and we want to pass from the high fidelity discretization, solving this high fidelity system a lot of time, changing the parameter to obtain the set of snapshots that are a representative set of solution of this high fidelity discretization. And we reduce these snapshots considering, as I said before, proper orthogonal decomposition. So we compute a small number of basis functions able to describe the high fidelity solution as a linear combination of these basis function with particular weights coefficient, so that the vector containing this coefficient are basically our new solution that we want to find. And also if inside this high fidelity model, we have some matrices of vectors that are parameter independent, in this stage we can also compute their reduced form and storage them to use in the online phase. Then in the online phase, we choose an instance of a parameter that we want to, with which we want to do the simulation. We assemble the reduced system, we solve the reduced system that obviously have a very much smaller dimension than the high fidelity one. So it's a cheap system to be solved. And then we can do all the post-processing that we want. So from here, we have the solution of the master model. Now we need to extract the solution at the interface and interpolate this data on the interface of the other domain, also considering, as I said before, the possibility to have non-conforming meshes. To do this, we use discrete empirical interpolation, with which at the same time we reduce the dimension of the data itself, and we interpolate very naturally the Dirichlet data from one surface to the other. As before, we have 2 different phases. The offline phase, in which first we compute the snapshots that here are the Dirichlet data already interpolated on the slave interface domain. So basically we have we are here where that is the data that we want to obtain after this phase. And then we apply to this set of snapshots the discrete empirical interpolation. With the discrete empirical interpolation, we get obviously the reduced basis function, and moreover, a set of indices that represent the degree of freedom from which we need to extract the magic points that are some value of the Dirichlet data that we want to obtain, that then we will use to reconstruct the entire Dirichlet data already interpolated on the interface of the slave domain. So basically we are here and we have these points that correspond to the magic points. And now we are searching the same degree of freedom, but on the other interface, so on the interface of the master domain. Obviously, here we are introducing an error because given the non-conformity of the two grids, we are not sure to find the same degree of freedom in both interfaces. But if we consider, as per the case of the B-domain torso model, a finer mesh on the master domain and a coarser one on the slave domain, then we are going to minimize the error that we are introducing in this way. And then when we have basically the magic points, or better, the degree of freedom in which we need to extract the magic point on the interface of the master domain, during the online phase, starting from the solution of the master model, we need to extract the solution in a small number of points that are the one that we are found using the discrete empirical interpolation, and we can use them directly to obtain, using the discrete empirical interpolation, the complete Dirichlet data already interpolated on the surface of the slave domain. So basically, we are passing directly from one surface to the other. And then we can apply this interface condition, obviously, on the slave domain. Then also the slave domain as the master domain can be reduced. This, as before, can be done considering the offline phasing in which we do the training. Then in the online phase, we choose the set of parameters or the parameters for the slave model. We assemble the reduced system, and here we are also adding the Dirichlet boundary condition coming from the discrete empirical interpolation. And then we need also only to solve this reduced system. And we can do all the post-processing that we want as before. So basically, we are dividing this reduction into phases, as we always do with the reduced model, an expensive offline phases, one for each part of the model, in which we are going to train our model. And then in the online phase, we combine all of this reduction to obtain a complete reduced order model of our one-way couple model with Dirichlet boundary condition. Obviously, in this way, we are reducing the computational cost, and moreover, we have also found a way to treat in reduced form also the interface condition, considering also non-conformity at the interface. And moreover, the other interesting thing of this method is that the interface condition take into account only the position of the degree of freedom of the interface on the interfaces, which means that we can use different finite elements to solve the master and the slave model in the high fidelity case, because we are not considering in the treatment of the interface condition the type of finite element that we are using in the high fidelity case. So just to give you an idea of the result that we can obtain using this method, this is a first test case that is time independent. So we have a parameterized master model coupled with Dirichlet boundary condition with a Laplacian, that is the slave model. This is a couple model solved on 3-dimensional domains that are 2 hollow spheres, in which the master model is inside the slave model. And these domains are discretized, as you can see, with different meshes, so that we have non-conformity at the interface. This is a reduction varying 2 parameters. Basically, you can see, first of all, that we can get, obviously, a good reduction in the dimension of the 2 systems that we are going to solve considering the reduced order model, which means that, obviously, we have a speed up in the computational cost. And in particular, the speed up is in the slave domain, because here, first, we don't need anymore to read the data from an external file. And moreover, here, we don't need to do all the post-processing for the extraction of the solution at the interface, which means that we can get at the end, for the complete couple model, a very good speed up in the computational cost. Moreover, given the modularity of this method, we are able to completely control the error that we are committing on the final solution. So this is the error, for example, on the solution of the slave model. And as you can see, if we are able to do a better reduction, a good reduction in the master model and a good reduction in interpolation of the interface condition, we are also able to do a good reduction and the reconstruction of the solution of the slave domain. So we have control on the way we are reducing and solving the model in all of the phases that we are considering. The second test case that is the most interesting in this case is the application of this method to the B-domain torso couple model. Obviously, the B-domain here is the master model and the slave domain is the torso. And in this case, we have tried to solve this model in 2 3-dimensional slabs that represent, for example, 2 portions of the tissues of the heart and the torso. Here, the reduction is only in time, and we are considering different discretization. In particular, obviously, the finer one is in the B domain. As before, we see a good reduction in the dimension of the system that we are solving, which means also reduction in the computational cost, especially as before for the torso diffusion model. Here you can see that the speed up is smaller than before. This is due principally because we are considering a small domain. So we have small meshes, and we expect, if we consider more realistic geometry, to get a better speed up than this that we can obtain in this way. But in any case, we see that we are in any case able to obtain a good reconstruction of the solution, reducing the computational cost. Then from here, we have tried to extend this method to two-way couple model, in particular, obviously, to reduce the fully coupled torso model. So introducing also the normal boundary condition to our B-domain torso model. This is the more complete model that we can use to obtain, for example, the electrocardiogram, and can be solved in different ways. For example, in LifeX, we have an implementation in monolithic form and one using Dirichlet-Neumann domain decomposition algorithm. The problem is that in these two cases, we need to use the same discretization in the two domains to have conformity at the interface. So here we would like to reduce this fully coupled model, also including the possibility to have, as before, the non-conformity at the interfaces of the two domains. And to do this, basically, we try to apply the same method that we have used before, but this time on the domain decomposition algorithm. So starting from the structure of the domain decomposition algorithm, to each time step we subiterate between the resolution of the two models with different boundary condition. In this case, we solve first the torso diffusion model, considering the Dirichlet boundary condition, and then the B-domain model, considering the Neumann boundary condition. And we subiterate between the resolution of these two models until convergence. And in this subiteration, we are going to apply the reduction. So basically, we are treating with the discrete empirical interpolation, so the reduction and interpolation, the Dirichlet boundary condition, and also the reduction of the master problem, that here is the torso. And then we need also to extract the Neumann boundary condition, reduce and interpolate the Neumann boundary condition, and then reduce also the slave model, that here is the B-domain. So the part of the reduction of the two model and the Dirichlet treatment is done as before, using the discrete empirical interpolation and using the same modular method. While for the Neumann boundary condition, basically we do as for the Dirichlet boundary condition. So we would like to use the discrete empirical interpolation, starting from the Neumann boundary condition already interpolated, in this case, on the slave interface domain. And to do this, obviously, we need to have a vector that contains the Neumann boundary condition. So we need to find a way to obtain this Neumann boundary condition that can be treated with this discrete empirical interpolation. In particular, here we are considering a weak formulation of the Neumann boundary condition. So starting from the solution of the master model, we compute the residual of the master model and extract this residual at the interface of the two domains. This vector corresponds to the Neumann boundary condition that we want to use, and then can be reduced considering the discrete empirical interpolation. So as I said before, we compute the snapshots with this Neumann boundary condition already interpolated. We apply the discrete empirical interpolation with which we found the magic points. And then we search for the corresponding magic points, or better degree of freedom, on the other interface. So basically, in the online phase, we need, after we have solved the master model, so the torso model, to compute the residual of the torso model, extract the residual on the degree of freedom that we have found with the discrete empirical interpolation, and then we can use this this value of the residual to compute the entire Neumann boundary condition already interpolated on the other interface. And then we can apply this Neumann boundary condition on the right-hand side of the B-domain model and solve the B-domain model in reduced form. Just to give you an idea of the numerical results, this is a very recent work. This is not the B-domain torso model, obviously. It's a heat equation that is solved in a slab divided into parts, into cube, and discretized in different way. This heat equation in these two different domains are solved with Dirichlet-Neumann domain decomposition, as I said before. And we have tried to apply this reduced order model. So basically, on the right, you can see two columns with two videos. The right one represents the high fidelity solution, while the one on the right represent the solution that we can obtain with the reduced model. Now you can see that we can get a very good reconstruction of the original solution using this reduced order model. And here we are doing a reduction, considering a reduction in time, but also changing the parameter alpha. So it's a reduction both in time and by the parameter. And from the point of view of the computational cost, this for us is it's a bit difficult to find a way to get a fair comparison between our model and a high fidelity one, because we don't have the treatment of non-conforming interfaces. So basically what I can say is that, first of all, if we consider here the complete solution of this model, considering the same discretization in the two domain, we can see that if we change the discretization in the two domain and treat the non-conformity, so the exchange of the boundary condition, considering the non-conformity at the interface with the discrete empirical interpolation, we can get, first of all, a speed up with respect, obviously, to the complete simulation with the same mesh. And the speed up increase if we consider the reduced order model, because obviously we are going also to reduce the two master and slave model that we are going to solve. So basically it seems for now that this algorithm is working also for as an alternative to Dirichlet-Neumann domain decomposition, where we are trying to treat the two domains with different discretization. So just to conclude, we have proposed a new reduced order method for one-way and also two-way couple model, especially Dirichlet-Neumann couple model, introducing also a way to reduce and interpolate Dirichlet-Neumann parametric data across non-conforming interfaces. And we have tested this method on time-dependent and time-independent model, and specifically for the case of the heart on the B-domain torso model. Obviously, there is room for more extension. We would like also to do the same for Robin data, interface data, and to extend this reduced model also to all type of two-way couple model, considering generic parametric interface condition. So with this, I'm concluding, and thank you for your attention.
Thank you, Elena, for this very detailed description of your approach to, let's say, virtual ECGs. Any question? Well, I would like to ask you one, not an easy question, but this is it. Many groups, many other authors have addressed this important application of cardiac models. In what way, in general terms, your approach differs from previous work in the literature? What is the main characteristic of main novelty of your approach?
Well, obviously, the reduction, that per se is, I think, the first time that is done for this type of model. And in particular, the fact that usually it's difficult to find also work in which they consider two different discretization on the two domain, because essentially the methods that are able to treat this non-conformity at the interface are very expensive. For example, we use this interpolation, but one can use the internodes, and that they are difficult to implement, for example. So basically, the possibility to consider non-conformity at the interfaces is something that is very important, and obviously also the reduction per se. So the possibility to obtain the same simulation, obviously reducing the computational cost, is something that is very important, because it is a very expensive model to be solved, especially if one considers real geometry and consider a real and complete torso, which is a very big domain. And if we try to discretize with a fine discretization, for example, the same discretization that we use for the electrophysiology, obviously we have a very big system also for the torso that is just a Laplacian, but it became very, very big to be solved considering classical technique.
Thank you very much. So thank you, Elena, and thank you.